Just in case, my battery lasts for about 6 hours, but just in case I plugged it in because of jet lag, and my my last rehearsal lasted over 2 hours. So it's good that we have an open mic after my presentation. Yeah. Thanks everyone for staying late for my talk. It's not really it's my and Alex's talk, and the work behind it. You might have seen some of our research presentations. We did a lot of security research in the firmware space, specifically UEFI space or Mac EFI or related. More recently core boot. We've done that back at Intel. Now we have. You probably haven't heard about this company. It's very new. We started the company a few months ago. It's called Eclipsio. And so the presentation today is discovering UEFI vulnerabilities at scale, or vulnerable UEFI systems at scale. And so what motivated us to do the research, and it's slightly different. It's more of a data analysis than looking for some new vulnerabilities in new systems. But the motivation is that we tend to focus, and we, meaning research community, and also us in particular, we tend to focus on trying to find new classes of vulnerabilities, preferably new systems. The more complex, the better. The problem is, even the newest systems today, a lot of them, they lack just basic firmware hygiene. They lack basic protections over the UEFI firmware that they have. Moreover, there's still lots of old systems in use, especially in the public sector. There are still systems that are 10-year-old, even running legacy BIOS, let alone UEFI or EFI systems. But definitely not the most recent 7th or whatever generation of Intel processors, the most expensive Dell or HP servers. Public sector runs very old equipment. And so there are tools currently available to test those systems for basic firmware protections. Like there's ChipSec that we've authored that can test if the firmware on a particular system is vulnerable. The problem with that is that in order to do that, we literally need to have all of that equipment to test it on, and that's not always possible. And also, it doesn't really provide us with a full picture of where the industry is in terms of basic firmware hygiene. So how do we understand the state of an entire population of all the systems? That's what motivated us to do this research. But prior to doing that, I'll just explain some basics in terms of how modern systems protect the UEFI firmware in the system flash, because we'll need that information later on. So system flash is something that stores your main firmware in modern systems UEFI firmware, but also other types of firmware like manageability engine firmware, like the embedded controller firmware, often like the persistent settings for network interface card, and other things. So there are two types of access that software uses to get to that firmware on the SPI flash. First is the direct access through memory mapped memory, through the memory addressable space. Basically, any address of a below a certain size underneath the 4 gigabytes is magically translated into the SPI read cycles on the SPI bus and get to the contents of the SPI flash. But this is only used for reads. It's used to bootstrap fetch the reset vector out of flash when the CPU comes out of reset. But there is another access, programmable register access, that the software is using in order to read or write to the system flash. And that's usually done through the memory mapped IO registers of the chipset, of a SPI controller in the chipset. With that, software programs the flash linear addresses explicitly into the registers, indicating to the controller or where exactly it needs to write to or read from. And so system flash can be partitioned into multiple regions. One region is the BIOS region, UEFI firmware region. Another is manageability engine, the embedded control region, GBE, and so on. But there is also this partition table called flash descriptor, which is also a region by itself. It's the first region that actually describes how the flash chip is partitioned. So that descriptor is the first 4 kilobyte of a SPI device, SPI chip device, located at the FLA 0. The way hardware or the way chipset determines that the flash is operating in the descriptor mode is it reads certain signature, and if it sees the signature, then it considers that at a 10 hex offset, then it considers that the flash is valid and descriptor is valid, and the flash is operating in the descriptor mode. So that descriptor, it's literally a partition table. So what it has, it describes all other regions, where those are located, what's the size of those regions. But it also describes who can access which regions. So there could be multiple masters in the platform that can access the same flash, and some masters should be able to access some regions, while others should be able to access other regions. And so that access control table within the descriptor region defines which master who can access which region in the flash, and which type of access, read or write access. So how that affects the security of the system firmware in that system flash? Well, first is what are the basic mechanisms that systems use to protect the firmware? The first is pretty obvious one. Every system, in order to maintain some basic level of protections of the firmware, it has to support signed updates. And in the UEFI case, those are typically signed updates are typically used as the so-called capsules, the signed capsules, which are submitted by the software to the firmware through memory or through file system to be flashed on reboot or upon resume from sleep state, from S3. And so those capsules contain multiple volumes as a payload. Those volumes could be the actual firmware volume that is being written or to the flash, but also firmware volume that includes executables that will be performing the update. So it's a rather flexible mechanism. The capsules might also include other firmware blobs, so not just the UEFI, but embedded controller and so on. So when that capsule is submitted through memory, if it's upon S3 resume, or through file system if it's upon a reboot, then when system comes up from reboot or sleep, it checks the signature of that capsule, authenticates it. It also authenticates the actual executable that will be performing the update, typically through a secure boot mechanism, and then writes the updates the contents of the firmware with the contents of that capsule. So that's the first basic mechanism. The second basic mechanism, obviously, is that the actual flash memory has to be write protected at runtime. Because if it's not, then the fact that your system implemented signed update doesn't mean anything. Because if the exploit can just directly modify the firmware on the flash, then they will be able to it would be able to modify the code that is performing the signature checks. So that's the other basic mechanism that has to be present on every system. And on x86 systems, there are a number of ways to achieve that. One is what Chromebooks are using. They basically just have a screw that asserts the write protect pin on these SPI devices. But most of the non-Chromebook devices, they use chipset-based mechanisms. One of them is the so-called protected range registers. The other one is SMM-based write protect mechanism. So basically, that allows software to update the flash at runtime only when that software executes in that special mode called SMM. And obviously, after checking the signature of what is being written to the flash. So that's the second mechanism. So obviously, the firmware has to be write protected. And the third protection is the descriptor itself has to be write protected as well. And the way it's achieved is this access control table within the descriptor is programmed at the manufacturing to prevent writes to that region 0, descriptor region, so it's self-protecting. And that happens only once. When descriptor is flashed into the flash chip, then software is not able to update that descriptor anymore. So that's how those protections are supposed to work, because otherwise, if exploit is able to modify the descriptor, then it's able to modify that partition table or access control table or other things, or just even break systems. So those are three basic mechanisms that have to be present on every system. And I'm not talking about any complex vulnerabilities in the UEFI or in SMM. Those are basic things that have to be everywhere. And so the usual way to check for those basic things is, let's say, run chipsec. There are modules in chipsec that just test for each of those. And so sure enough, a lot of platforms, even the newest ones, they fail those tests. For example, we did the tests on the Skylake-based MSI systems. They failed. Alex Matrosov recently did the analysis of gigabyte systems, bricks, and those failed. We also did some core boot analysis on systems that have core boot, not Chromebooks, but just random systems, and those failed as well. But again, the downside of this approach is that it requires actual running it on actual equipment. So that's not scalable. We want to scale to understand the whole picture without playing this whack-a-mole game of testing on every single system and finding the same things again and again. So that's why we started that analysis. So first is how we can achieve that. So we have tons of UEFI images available to us through the websites of manufacturers. Can we actually use them to test for those basic protections? Can we find out which systems lack those protections just based on the analysis of the update images? So we're not the first who did this type of research. Teddy Reed in the past 3 years ago, he did an awesome research where he essentially applied a lot of analysis to tons of update images that he downloaded. And as part of that research, he released a number of tools, including Sub-Zero, including UEFI Spider. A lot of the ways that UEFI Spider gets the images don't work today because vendors changed the way they publish update images, so we had to fix that, a lot of that. But we have used UEFI Spider, among other things, to actually grab all the scrape all the websites from all the vendors and get all the updates. There are also tools that can parse the images because in order to do some analysis or any analysis, you need to parse, you need to extract firmware volumes and so on. So the Teddy has a UEFI firmware parser. Nikolai Schley has a UEFI tool or a UEFI dump specifically utility that can do that. Chipsec also does that, so you can use either of those tools. So, but let's continue. So this is essentially what we based our research on, and we're trying to remotely screen all of the firmware update images for certain problems in order to find vulnerable systems. Remotely, we can call it tele screening, right? So, or even shorter telescreen. Some of you folks might appreciate this, especially here. So the idea behind that analysis is, what if we find firmware update packages that contain images, firmware images, that are not capsules, but images that include full valid SPI descriptor? What does that mean? That means that those images are most likely, after filtering, of course, false positives, most likely those images are full SPI flash images. And so those are primary suspects for us, because that means that the update for the firmware update is distributing the entire SPI flash ROM image, which may be an indication that there is no signature on the system that this update is intended for, and there's no write protections of the system flash that this update goes to. So that's easily automatable. But the problem is, a lot of updates include those images for different reasons. So we actually need to understand, once we have this set of suspects, we need to understand if the update is actually using that image for the update, or if that image is for whatever or other reason. So that's a little bit more complex. It's less easily automatable. But once we find those candidates, what that tells us is that the update mechanism is using entire ROM image, which means that they're not signed. And if they're not signed, that means that most likely means that the system flash is not protected, because if you don't implement signed updates, why would you protect the system flash at all? And in a lot of cases, and I'll explain why, in a lot of cases that also means that the descriptor is read-writable. So we essentially, if we find those candidates, then we find systems that have those three basic vulnerabilities there. So the whole process looks like that. We just download a lot of firmware updates from vendor websites. Then we extract all sorts of binaries from those updates, update packages, which look like firmware images. Then, of course, we get a lot of candidates firmware images, but not all of them are really firmware images. Some of them are just weird binaries. So we need to filter out the binaries that are really firmware images. And after that, we need to understand if those are UEFI images or full SPI images or BIOS images and so on. So we need to parse and analyze those. So that looks rather simple. So this is what essentially we did. We've downloaded approximately 33,000 firmware update packages from 9 vendors. Some of them had better coverage than others, but it's been a pretty significant amount of update packages that we got. We've extracted 44,000 different candidate images by filtering them through known binaries used in the updates, like ROM, bin, IMA, cap, and so on. Basically, the typical extensions used by the vendors for the firmware images. But we also applied some other things because sometimes extensions are not enough, so we applied some basic heuristics, looked for known magic values, and looked whether the image looks like a UEFI. For example, it has some FVH, firmware volume, signatures, and so on. Then after that filtering, we've got 21,000 unique UEFI firmware images. And there were duplicates, so that's why the number is lower. So 21,000 unique UEFI images. We've parsed them, analyzed them. The rest of the images were also legacy BIOSes. So one thing in this process is that it's supposed to be, or it should have been generic. It should have been simple to extract those images. But the reality is the update packages they're not equal to the actual firmware images that you need to analyze. So there is no standard format. So for examples that we've seen that update packages include all sorts of utilities for different OSs like DOS, UEFI shell, and Windows and Linux and so on for update. Then the firmware images in a lot of updates were encrypted, or in some updates were encrypted. So we actually had to understand how to decrypt those. How does the update package decrypts those? Then there were multiple types of firmware images for the same update, but used in different cases, in different ways the update applied. And also, in a lot of cases, we've seen that the images were just plainly embedded into the executables. So all of those had to be somehow understood, comprehended, and in order to just even extract the suspected images. The algorithm was rather straightforward. So we try to apply we try to understand if it's just some sort of a known archive, and we decompress it. If it does work, we use binwalk. Sometimes use vendor-specific utilities. Sometimes the vendor updates had a special command line argument in order to extract images out of the update that we found it and we could use. And also other things like, for example, just monitoring the file system, how the update changes file system and where it drops the contents of the update package. So after all of that is done, we need to search for SPI descriptors in the images because we need to find those full SPI ROM images. In order to do that, we've excluded known capsules, cap, FL type of images from the updates. We only included images with the exact size of a SPI flash chip because we're interested in a full SPI image. We only included images which contain a valid SPI flash descriptor and also rewritable descriptor. So the valid flash descriptor has a couple of conditions. First, it has to have signature at the offset 10 hex. Then it's not really sufficient to look for just a signature because there are spurious signatures all over. And so we've looked for the reserved bytes in the descriptor or all F. So basically, basic sanity checking. Rewrite access to the SPI flash descriptor is basically defined by that access table that I mentioned previously. So we've looked for the images that contain descriptor, which is read-writable. Basically, this first RW value CPU can read-write to the SPI descriptor. As a result of that, we've got out of 21,000 unique UEFI images, we got approximately 3,500 full SPI images, and those are primary suspects. So that's approximately 17% of all of the images we actually analyzed. But what stands out is that there is a disproportionate, there's a difference from vendor to vendor. Some vendors did not have SPI full images at all, like Intel, for example, or Acer had very few older images. Some vendors had more, but still kind of a lower number of full SPI images like Dell, HP, Lenovo. But there were a few vendors like Gigabyte, MSI, and Asus, to a lesser extent, that had a huge amount of spy images within the update packages. So obviously, all of those don't necessarily mean vulnerable systems automatically. There are false positives. Not all update packages which have full spy images are indicating that those systems are vulnerable, because there could be some updates had both capsule and a full spy image. And when the update is happening from the at runtime, then the update is using capsule, but then this full spy image is included for some other purposes, like potentially used at manufacturing, but not during the update. So that could be a false positive, or in some of the updates included full spy image, but only used with the user interaction. Basically, when you reboot the system, you enter the BIOS settings, and then you update the flash from that image. But it requires user interaction, physically present user. So those are kind of false positives. Also, there are false negatives. There are things that we've missed for sure. For example, the fact that the signed capsule is in the update package, and we consider it as a non-vulnerable update package. It doesn't really mean that the system isn't vulnerable, because what we've seen in the past with Asus, for example, is that they implemented a capsule update, signed capsule update, but they have not implemented write protections over the system flash in Ivy Bridge-based systems in the past. So we would miss that through that analysis. There were also updates with the images that we just couldn't extract. And also, we've excluded read-only flash descriptors, but those may indicate vulnerable systems too, in case if update ignores descriptor. So those would be false negative as well. And capsules don't necessarily have to be signed. So capsules, there may be older systems that use capsules without signatures. But ultimately, doing an additional analysis over all of those suspects yielded certain the results you can see here. So we've found ultimately over 500 modals through that analysis that lack basic protections of the EFI firmware. Some of those are older. For example, ASRock or ASRock, they had 73 images that are potentially vulnerable, which correspond to 53 modals, but all of those are older than Skylake. All of those are older than 2015. Asus had 600-ish potentially vulnerable images, which correspond to 61 modals. All of those were older than Ivy Bridge. So basically, Sandy Bridge and older, so 2012. A few vendors had a smaller amount of modals that appeared to be vulnerable, which indicate that they might have just forgotten to implement, those protections on those systems. But you can see that there are some of the vendors like Gigabyte had over 1,000 potentially vulnerable images, including 345 Skylake and above. That's 2015 and above, corresponding to 247 modals that lack basic protection. So that's pretty much almost every system that they have. MSI, same thing, 1461 potentially vulnerable images corresponding to 98 modals. 495 modal images are Skylake and above, so those are vulnerable. Lenovo had potentially up to 26 modals that we found potentially vulnerable, and those are primarily ThinkCenter, Idea Center, and ThinkServer. They used full spy image for the update, or they appeared to use full spy image for the update. So a few examples. MSI is what stand out. As I mentioned, it's almost 500 Skylake and above images vulnerable, total almost 1,500, and corresponding to approximately 100 modals. We confirmed on some of the systems because that was a big, huge number, so we actually went and confirmed on some of the MSI systems, and sure enough, they don't have any protections. So one thing was interesting is that they provide a live update utility through the software that can update their UEFI firmware, and you can see that what it does, it's online update of BIOS and firmware, auto detects and suggests the latest BIOS firmware. That's exactly what we need, a live update over the network of a unsigned BIOS firmware on those systems. And in addition to that, you can see that antivirus software is actually conflicting with that tool, so it has to be disabled as well. So that's a very good live update of Trojanized firmware. So Dell, we had 78 suspects corresponding to 24 modals, but 13 updates corresponding to 4 modals appeared to be false positives because they had capsule and a ROM image, raw ROM image together. So the ROM image is probably used at manufacturing, and capsule is used in the actual update. So right now we suspect up to 51 update packages and 11 modals that seem to be vulnerable. Most of them are Inspire and Vostro, older modals, older than 2014, but with updates up to 2016. We're still investigating some of the others in Dell. Lenovo, as I mentioned, mostly ThinkServer and ThinkCentre Idea Center modals, also older ones, although ThinkServer had rather recent 2016 updates. So you might look at this utility that Lenovo provides for firmware updates, and what's interesting is that this is probably the longest support period of a utility of a software tool I ever saw, 1984 through 2016. That's how long they support that flash update utility. Yeah, the interesting thing is that they started in 1984 as well. So with that analysis, we seem to be able to at least come up with the vulnerable modals, or modals of systems that lack basic protections, which is important. But we also, through that dump of update images, we can do other things. We can start building a list of known executables in the UEFI space, and we can apply it to monitor changes in the firmware. So, for example, we cannot, if we want to monitor a certain change in the UEFI firmware, we cannot just compare hash of the entire firmware image, because there are so many modifiable data there, the NVRAM and ACPI tables and certificates and a whole bunch of other things that would be pretty useless. So basically, we need to extract all the executables out of the every EFI image, and we need to compare those executables against the known list. So what we found is by extracting executables out of those 21,000 unique UEFI images, we've been able to build this global whitelist for those 9 vendors, and the 10th vendor is kind of a work in progress by the community at the moment. So we also kind of got some interesting numbers. For example, there are 45 to 90 unique executables per update, but at the same time, there are about 100 to 300 unique executables in your firmware, so which means that the updates are typically much smaller than the actual entire image, which is understandable because the updates are typically capsules and don't include everything. So now, based on that data, we can build this whitelist or a list of known executables. So how do we actually do that? What hashes we're going to use? The plain hash over the entire PECOF image, or the authenticate compliant hash, or something else. For example, most of the platforms in the UEFI, they support authenticate hashes for most of the functionality, like Secure Boot, like TPMs, basically not except that UEFI firmware submits authenticate compliant hashes to the TPM. So we can build the whitelists through all of those type of hashes. So and that's what we did. We built approximately 2 million global whitelists based on plain hashes, but also authenticate compatible hashes. And we've built another whitelist that contains approximately 1 million executables, unique executables, without authenticate hashes, but in addition with the time date stamp field in the PE header masked off. So the authenticate, I probably will just just skim through. The authenticate hash is the way Microsoft specified how to calculate the hash of the PECOF executable. There are certain fields that are masked off and not included into the hash, like checksum or certificate table entry, and so on. So that basically provides a way to uniquely identify a PECOF executable regardless of the checksum. Exclude some of the data which is not really needed. So in addition to that, you can mask off the time date stamp, so that would essentially eliminate duplicate executables which were just built at different time but haven't really changed. So that's why there are fewer executables in the whitelist with the authenticate plus the time date stamp cleared. So that's some statistics over the unique UEFI hashes that we gathered through that analysis. You can see that 1,900,000 plain hashes, 1,800,000 authenticate hashes, so approximately the same number, and lower, twice as low of authenticate hashes with timestamp cleared. So now with that whitelist, and the part of the whitelist is open source right now on a GitHub. Other parts will probably be publishing those soon, but now what you can do is you can actually check your firmware against that known list of UEFI executables and find if anyone added any extra executable that shouldn't be there. It's not fully perfect because there are false positives, and Alex, for example, he ran that global whitelist against his Lenovo 450, I think 430, and found one single executable that wasn't in the whitelist, so he freaked out. But after about 4 hours of reverse engineering of that executable, he figured that this was a false positive, that was a Lenovo EM SecPI legitimate image with a small change only on that particular system. And none of the hashes detected it. None of the hashes, not the authenticate, not the plain hash, had that hash of that executable in the whitelist. So obviously it's not foolproof, so it can give false positives as well. But in addition to building the whitelist and checking the firmware against that whitelist, we can also start gathering statistics on interesting components and features, and statistics on which systems support or enable those components or features. So, for example, you might remember absolute compute trace, which is kind of a firmware-based anti-theft technology, but can be of dual use, and there was some controversy about this technology. What it does, it actually embeds a lot of executables into your firmware, but in addition to the OS. So what we did is we decided to apply a very complex heuristic to find systems that support CompuTrace. We decided to search for word CompuTrace in the name of the executables. And so we found 39 different Dixie and PI modules used by CompuTrace on the UEFI-based systems. Some of them specific to specific vendors like Lenovo, others are more generic, present in several vendors. And we can now start gathering statistics for those type of components or features across all of the entire population of the system. So in the CompuTrace case, we found 17,500 CompuTrace modules across the 9 vendors, which were corresponding to approximately 7,000 unique UEFI images. Which means that two and a half components on average in each UEFI image corresponding to the CompuTrace. Those were rather simple kind of heuristics that we've applied in all cases, both in detecting those basic protections, missing basic protections, as well as building the whitelist, as well as searching for kind of a specific component. So we can improve that. We can improve. We can detect. Better detect capsules. We can explicitly detect that the capsules are present, not just by a simple heuristic versus the full SPI image, but more more precise things, like, for example, detecting the firmware update Dixie driver, detecting the system firmware descriptor PI module, or detecting the image authentication structure in the capsule, which contains the actual PKCS7 signature for the capsule. We can also start detecting within the images that they support signed capsule updates and they support secure flash update, because there are certain Dixie and PI components that are responsible in UEFI-based systems for implementing those capsules and secure update, and those are like the FMP authentication lib as part of capsule update, capsule package. Also, PCH BIOS write protect. Those are modules can be responsible for protecting the SPI flash. So we can start detecting those, and those would be more precise. So as a conclusion, this even simple analysis of a huge chunk of update packages can yield certain results, can find systems that are that lack basic protections of the firmware without the need to actually purchase those systems and run tools on them through just the analysis of the updates. What we've learned is that some vendors have had those basic protections for a while, like Dell, like Intel, like HP. Some vendors started recently, like Asus or ASRock, and others haven't even started yet, like MSI, Gigabyte. This kind of a type of analysis is not perfect. There are false positives, there are false negatives, there are room for improvement. And it also can be applicable to finding other vulnerabilities, more complex things, not just basic protections, but more complex things like S3 boot script vulnerabilities, SMI issues, and all of those, without the need to get the systems, physical systems. So with that, I think that's pretty much it. Thank you.